Hi guys, so today I'm going to do a video on how we take the sum of functions. So last lesson, or I say last lesson, you guys haven't actually done this lesson yet, but when you see this video you will. Last lesson we talked about absolute value functions, and now we're doing the sum of functions. So remember, the word sum in mathematics means add, so we're going to add them together. Now, for some reason, the syllabus mentions the word sum of functions, but technically subtraction is a form of sum, so we're also going to look at the difference of two graphs. So the sum of functions, there are two methods that can be used for the sum of two functions. The bad method, which is the algebraic method, and the graphical method, which is the easy method. So the algebraic method states that if you have two functions f of x and g of x, by adding the functions together and simplifying, where possible, we will get the function f of x plus g of x, which can be graphed. So for example, if I have the graph y equals f of x plus g of x, where f of x is the cubic function x cubed plus 1, and g of x is the parabola x squared minus 2x minus 3, then f of x plus g of x would be simpler than you think. It's just going to be x cubed plus 1 plus, and that's our f of x, and then g of x is plus x squared minus 2x minus 3. And then we could simplify and we get x cubed plus x squared minus 2x minus 2. Now, it's mathematical convention to start with our highest power of x and then decrease. Not sure why, it kind of just looks a bit neater. Now, at the moment, with your ability to not do calculus, you would have a lot of trouble, and I would without calculus, would have a lot of trouble graphing this, and we can't. So we can factorize this expression. Does take a while, but let's have a go. I might take out a factor of, let's take out a factor of x from these. So I'm going to have x and then x squared minus 2. And then over here, 1 minus 3 plus 1 is minus 2. So I'm going to have plus x squared. So I've already used these ones. So I'm going to have plus x squared minus 2. And then I can take out, I might change the color, a common factor of x squared minus 2. And then I'm going to have x plus 1 because we've got that invisible 1 there. So my intercepts are going to be x is equal to minus 1, or x squared minus 2 equals 0. So x is equal to plus or minus the square root of 2. So I'm going to have minus 1 or plus or minus root 2. If I graph that, well, root 2 is about 1.4, I believe. Let me check on my calculator. Yep, 1.41. So root 2 is going to be about here. We've got that. We've also got minus root 2, and we've also got minus 1. Then I go, oh, okay, this is a positive graph, so it's going to look something like this. And we also should consider our y-intercept, which is going to be minus 2. So my graph is going to look something like this. And that's going to be there. Okay. So that's one way of graphing f of x plus g of x. But sometimes it's not that easy. That was an easy example of using the algebraic method. But for example, if I had something like find f of x plus g of x, and let's say it's equal to, let's say f of x is equal to x squared minus 1, and then I got to add 2x plus 1. Well, how on earth do we graph that? And that's a good question. I would have asked myself that as well. This is where we use, and we're going to do this same example that we just did in red. This is where we use the graphical method. So the graphical method I've put in is a better method because it's a method I'm going to prefer you guys to use and practice and get to know how to do properly. So by drawing the graphs of the two functions f of x and g of x separately, we can add the ordinate. So that just is another way of saying y coordinates. So we're not going to add the x coordinates, just the y coordinates, and we call those ordinates. So we can add the ordinates together to produce the graph of y equals f of x plus g of x. So what we do is we sketch the graphs separately, and then we add the two graphs on our graph. Now this is where we need to have a bit of abstract thinking here, and we've got to physically think about what it means to add these two graphs. We do that by considering not the x points, but the y points. So for example, if I'm here, right here, what I've just done, and it might be easier if I do that in black, right there. Both of those graphs have the y value of 0. So if I plus those two graphs together, I'm going to get 0 plus 0. So my graph is still going to be there because 0 plus 0 is still 0. Now, then we've got to consider at a few other points on our graph. If I have a look down here, over here at the y-intercept at 3 for my parabola, well then I've got 0 plus some really big number up here, and I don't know what that is. But 0 plus a really, really big number is going to be a really big number. So my graph is going to exist up here when I add them both. I might say that again. So the blue graph exists down here, but my red graph exists up here. The blue graph has a y value of 0, and the red graph at that point might have a y value of 100. 0 plus 100 is 100, so my graph at this point is going to exist up here. Probably even further up, but it's going to exist up there. Then I might consider what happens down here at the vertex of this parabola. This is a y value of -4, and if we look up, this has a y value of 2 at this point. Simply, we add the y values together. 4 plus -2 is -2, so my graph is going to exist here. All I've done is I've literally added the two graphs together. So at that point, we have -4, and we also have, for the blue graph is -4, and for the red graph it's at 2. If I add -4 and 2, I get -2. Let's consider a few other values. Here I've got down here I've got -3, and up here I've got 1. -3 plus 1 is -2, so my graph is going to exist here. What else do I have? I've got my graph. Well, I reckon my graph about, just look there. Yep. I reckon my graph here, and here, I reckon they look about the same. They look like they're both at an equal distance, or around an equal distance, probably even a bit closer. They look like they're about an equal distance from the y-axis. So let me just check what we had up here. So it was at -1 and √2. So, actually let me pause there. They don't look the same here. But I can see here, moreover, that if I look at here and here, we can see that those two graphs are exactly the same distance from the y-axis, from the x-axis as each other. They're exactly the same. So if we add, say, -2 with +2, I get 0. So we're going to have another intercept here. Now we expected that, which is why I was looking up here. We expected another one to be there because we had already graphed this one. We expected one to be at -4 and √2, and that's what we see here. So again, I made a little mistake there. That and that, they don't look quite the same. They do look very similar, and I would reckon our graph, if we plus them together, it would be about here. But it is more obvious that these two will be the same. Now we have to consider what is happening down here. So we then think, okay, which one is going to be increasing or decreasing faster? My parabola or my cubic function? Well, a cubic function decreases or increases faster than a parabola because the power of x is bigger. The power of x is bigger than x squared. So for example, why I'm saying that is this negative value, these negative values down here are always going to be at the x coordinates larger than the y values for the parabola. So that means if we add them together, for example, if I added, I've got -4 down here, but on this part of the graph, I'm only up here at 2.5 or whatever it is, 2.5, which means my graph is going to go down like that, which is what we expected from that graph. Most of the time you won't have this other graph drawn, but it's good to look at our two different graphs so we can compare. Again, I might say that again. So here we can see, at this point down here, the y value on the cubic function, which is the red function, is -4. But on the blue function, the y value is only about 2. It's just above 2, about 2.5. So -4 plus 2.5 is still a negative number, which means our graph is going to exist in the negative part. Okay, now we have to consider whereabouts on my graph does the y value on the top and the bottom be the same. And I'm feeling like it looks like it's about here. So we're looking on our graph, where does the y value and the x, where does the y value on both of the graphs look the same? Because when they look the same, when they're the same distance from the x-axis on the top and the bottom, then when we add them together, we're going to get a y-intercept. So it looks like it's about there. We don't have to be too exact with these graphs. It looks like it's about there. So I know that my graph's going to go down here. I'm literally just connecting the dots now. Down here, it's got to go down there, up there, and now it's going to go up like that. So let's rub out all of that unnecessary stuff. We've got that, and that's our graph. I'm going to go over it in highlighter. So that's our graph there. So what we're doing is we're literally looking at the graph and adding the two functions together. We're going and looking at the y values. So for example, to find this x-intercept, we looked on my graph, where does it look like the y value of the red parabola, where does it look like it equals the y value of the blue graph? And it looks like it's about there. If we added +4 with a -4, which is about down here, we're going to get 0, which is why our x-intercept occurs there. And that's our graph. Now in an exam, then what I would do is I would leave my working out there, because the marker wants to see your working out in case you make a mistake in the final part over here. So you're going to draw your points, and you're going to go, okay, my graph goes like this. And that would be your answer. Now you may think, why can't I just do that? Good question, but remember our graphs can get a bit more difficult. So this is the graphical method. It is the better method to use, and we need to get good at it. So we're going to use the graphical method to do a few examples. So we're going to sketch the graph of y equals f of x plus g of x, given that f of x equals 3x plus 2 and g of x equals x minus 1. So let's, first of all, if we think about it algebraically, f of x plus g of x is going to be, if you figure it out, it's going to be 4x plus 1. Now we know how to draw that graph. More exaggerated, it might be more clear. So if I draw it further apart, we might do that again. So 3x plus 2, so I might go over here, minus 1, minus 2, minus 3, and I might go 1, 2, 3, 4, 1, 2, 3, 4. That graph was probably too small to do that question, so it wasn't very clear what was happening. So let's graph again, 3x plus 2. So I'm going to have 2, and then minus 2/3 is going to be there. So we draw that in. And then we go x minus 1. Oh, I know why that one didn't work. X minus 1 does not look like that. Sorry, people. That's why it didn't work. So, we have minus 1, and then we're going to have 1, so we'll draw that in. If I'm smart enough, I might cut that out of the video, but I don't know if I know how to do that. So, we can see that if we look along the y-axis, and I should draw y and x, if we look along the y-axis, then here we've got minus 1, here we've got positive 2, and if we plus those together, we get positive 1. Okay? If we look, say, I reckon about here and here, they look like they're the same distance from the y-axis. So if we add those two graphs together, it's just going to get 0. So we're going to have our y-intercept about here. Now, what's happening here? Well, we've got a red value of 3, and then down here we've got a value of about minus a half. So it's going to take, not the whole bit off, but it's going to take a tiny bit off. And then when we get to here, we've got a value of 0 here, and then a value of about 4 here. So 0 plus 4 is 4. So at this point at the graph, where our x minus 1 cuts the x-axis, we've got 0, and then up here we've got 4. 0 plus 4 is going to be 4. And then if we go along, well, over here, for example, we've got this. This is about 5, and then down here is about 0.5. So if we plus them together, we're going to get 5.5 up here. And then if we keep doing that, the two red graphs are going to keep plussing onto each other, and overall they're going to make this blue graph that I'm about to draw bigger and bigger and bigger, which is why we get this. And then I get rid of the red bits, and we have 4x plus 1. Now that graph is very easy to draw without doing the graphical method, but it's good practice doing the graphical method. So let's have a go at this one. I'm going to kind of abandon ship on these graphs because I don't like them. So I'm going to do them to the side. So we've got y equals minus x squared minus 4, and y equals 2x plus 2. So if you want to do your graphs maybe in this section, or if you can figure out those graphs, they're a bit squished, you can. So, let's graph minus x squared minus 4. We know it's a sad parabola, and it has y-intercept of minus 4, and then it's just looking really sad, like this, going down like this. And that's at minus 4. And then we've got the line y equals 2x plus 2. So if that's, we mark that minus 3, minus 2, minus 1, 1, 2. I know I said you don't have to make your graphs accurate, but when we're adding and subtracting, multiplying and dividing graphs, it does make it a bit easier if your graphs are more accurate than we did for reciprocal functions. So 2x plus 2, we're going to put a 2 here, and then that's going to have an intercept of -1. So that's my graph there. And then, okay, we're just got to think about what's happening here. I like to start on the y-axis for all of these questions. So is it black? Remember, I'm colorblind. The black graph, it looks kind of green, but the black graph starts on the y-axis at 2, and we've got one on the red graph that's at -4. If I add those two together, I'm going to get -2. So my blue graph that I'm going to start drawing is here at -2 on the y-axis. Yep. Okay, so what else shall we consider? I'm thinking that my parabola is decreasing much, much faster than my straight line. So my parabola down here, for example, might be at -10, but my straight line is only up here at about 6. So what I reckon is going to happen is I reckon our line's going to go up a tiny bit and then go down. I reckon that's what's going to happen. So again, we can add points if we want to, but this one's a bit difficult because the parabola is decreasing so fast. So if we get this point 3, and then we add, say, -5, well, 3 minus 5 is -2, so it's going to be about here. But it's going to get a bit more dramatic as we go, say, over to 4. So 4 has a y value of about 10. So we've got 10. But then, if we think about what 4 is, -4 squared minus 4, so that's going to be -18. So 10 plus -18 is -8. So this is going to be all the way down here. So I like to test a few points like I did just there, plug it into both of my graphs, add them together and see what happens. I can see that my graph is going to start doing this. The parabola, every single time you go up an x value, it exponentially is increasing the y value. So it's definitely going to trump the little straight line. So it's going to go down. And then what's going to happen is, well, the same thing's going to happen on the other side. It's going to be a bit more drastic. So we can see that, well, let's say I've got this 0 value here. This 0 value, I might do that in red, of -1. And then if I add whatever's down here, let's say it's -5, -6, let's say it's about -7. Well, then 0 plus -7 is all the way down here at -7. So my graph is going to start decreasing a bit more drastically than it does on the other side. The reason it's more drastically is because you've got two negative graphs. You've got two negative graphs. And if you plus a negative with a negative, you're going to get an even larger negative number. So for example, if we look at this number here with this number here, let's say this one is about 2, -2, and this one down here is about -7 or -8. You plus those together, you're going to get about -10. And as you keep going, it's going to keep decreasing and decreasing. So that graph is going to look like that. And if I rub out all of the old stuff, our graph's going to look like that. Alright, I really like those questions. What have we got next? Oh, is that all I had? Let's do another one. And let me just make up one. Y equals, I don't know, x cubed plus, I probably should call that f of x. Actually, I might get an exercise question. Just bear with me while I do that. Get up an exercise question. That would be better. Almost there, sorry. Okay, let's add the graphs. So this is exercise 706, and we're going to do, let's do question 1e. F of x equals 3x minus 4. And g of x equals x squared plus x. Oh, I said that wrong. Sorry, f of x is 3x minus 4, and g of x is equal to x squared plus 2x minus 2. Okay. So again, we get our trusty old Cartesian plane, and we graph both of them. Remember, following conventions, we've got y and x. Again, when we're doing our plussing and minusing of graphs, it is easier for us to be a bit more accurate than when we did reciprocal and square root functions. And unlike reciprocal and square root functions where we didn't really consider individual points, sometimes it is easy to consider points just to see what's happening. And of course, it's always beneficial to consider your extremities like 100 or minus 100 or 1,000. So 3x minus 4 I'm going to do in red. We're going to have a minus 4 here, and we're going to have cross the x-axis at 4 over 3. Now 4 over 3 is like 1.33333, so it's going to be here. A very straight line. And then x squared plus 2x minus 2. Well, let's factorize him. Oh, I don't think you can factorize that. Okay, let's use the quadratic formula then. So x is equal to minus 2 plus or minus b squared minus 4ac. So 2 squared minus 4 times by minus 2 is 12. So root 12 over 2. So minus 2 plus root 12 over 2 is 0.73. And then minus 2 minus root 12 over 2 is minus 2.73. Okay, awesome. So they've got a parabola. We've got about 0.73 as one intercept, and minus 2.73 is another intercept, and minus 2 is our y-intercept. That's a very weird parabola, but we've got that. Wish they gave us one that factorized nicely, but oh well. So let's consider what's going to happen. Again, I like to start on my y-axis. I might change to black. So let's start on my y-axis. Here I've got a minus 2 and a minus 4. If I add them together, I'm going to get a minus 6. So I'm going to have minus 6 down here as my new graph. If we consider, say, let's say this parabola here, and then we're going to add this part, well, it's going to be then 2 negatives, so it's going to be even further down there. So you've got, for example, minus 2.5 plus minus 6, minus 8.5. So we're going to be about down there. But then, if I notice on the left-hand side, so my second and third quadrants, I've got a parabola up here. And we know a parabola increases much, much faster than a linear function. So my graph, yes, it's going to start going down here, but then it's going to start going up like that. And that's because, so remember, our parabola increases very, very fast, and our linear function decreases not very fast. So if we add them together, for example, if I'm all the way down here, but if I'm down here, my parabola is going to be quite all the way up here, which is quite further. And it's going to be even more drastic as we go along. So if I moved all the way and just exaggerate to prove a point here, then my parabola is going to go up much, much further. So if I add those two together, we can see that it's going to be up there, because our parabola increases so much faster than a linear function. So it's going to go up like that. I don't know when it's going to do that or where, I just know it will. Okay, so that part of the graph's done. Let's consider what's going to happen after that. So what question? I've lost the question. It was question 1E. So, sorry, just 2 seconds. Yeah, so 1E, so then we've got a few things happening. We've got, up here, I've noticed that we've got 2 bits up here that are in the positive part of the graph. Now, if I add 2 positives together, then I'm going to get an even larger positive number. For example, let's consider here. This is about, say, 1.5. And then up here on the parabola, well, you've got, say, 5, 6, about 7. So 1.5 plus 7, well, that's going to be 8.5. So I know my graph is going to go up into the first quadrant eventually. So it's going to go up here eventually. We've got to think about where it's going to cross the x-axis, and we do that by considering where is my graph equal in distance from the x-axis, and it looks like it's about here. I might do that in red to make it more obvious. It looks like it's about here. So we can see here, if I zoom in, that the blue parabola is about the same distance from the x-axis as the red linear graph. So if we add those two together, say it's going to be 1 plus minus 1, we're going to get 0. So my x-intercept, sorry, is going to be there. So it's going to go up, it's going to go up like that. So we can see it's a parabola. Now what I like to do is with these ones that are a tad easier to add algebraically, let's consider, well, that's going to be x squared plus 2x minus 2, that's f of x, plus g of x, which is 3x minus 4. I think it was the other way around, but it doesn't matter. And then if I go x squared, it's going to be plus 5x minus 4, 5, 6, 7. Yeah, and that pretty much looks like what we had. Now, yeah, it is easier to do that algebraically, but I want you guys to practice doing it graphically, because the hard questions, you have to do it graphically. Let's see in the exercise, for example, and I'm going to leave those to do yourself, but for example, G and H, you might have to do graphically. If you're unsure how to graph G, so 1G, if you don't know how to graph G of x, what I would do is just use GeoGebra, because I know you haven't done cubic functions, you're going to do it soon, but just use GeoGebra to figure out what x cubed plus x plus 7 is. And for H, yeah, you might want to use GeoGebra again to figure out what x cubed minus 4x minus 1 is, just because you haven't learnt them. Not as important. As we get through the course, we'll have other methods of graphing, especially when we get to the calculus of graphing. It really helps us in graphing. So if you're feeling a bit stressed that you don't know how to graph cubic functions, we're going to be doing calculus that allows us to find turning points and stuff, for example, that makes graphing them really easy. So the addition of functions can be a bit funny graphically, but it's a really useful skill. Now, I can't see any questions in the textbook on the subtraction of functions, but I just want to quickly talk to you about them, just in case, I don't know, in the HSC maybe they'll do one. I don't think it's officially in the course, but technically the subtraction of functions is just the inverse of the addition. So I don't see why they can't, because, yeah, as I said, subtraction is just negative addition. So let's have a look. So f of x, and we've got minus g of x. So I might go subtraction, just do the quick heading. Subtraction of functions. Why did it do that? Sorry. of functions. So for example, f of x, y is equal to f of x minus g of x. The easiest way to do this is to graph the negative of g of x and then add as normal. So what do I mean by the negative? Well, all I mean by the negative is, for example, if I had the parabola y equals x squared, well, it looks like that. Well, then to graph the negative, well, it just looks like that. So we're just literally flipping it upside down. If I had a more complex graph, let's say I had this graph, well, then the negative would just literally be flipped upside down, which would be the red graph, and that would be its negative. If I had a more common function that you might see, like a cubic function, like this, well, then the negative, well, if you flipped it upside down, it's actually going to look like this, and that's y equals minus x cubed. So what do I mean by graphing the negative then when we add them? Let's do an example. So just do this somewhere in the booklet or in your page, because it's a good skill to have. So we're going to, question number 1, we're going to graph y is equal to f of x minus g of x if f of x equals x plus 1 and g of x equals x squared. So as I said, we can't subtract functions if I were just to graph these two. Well, I mean, we could graph them, we could subtract them, but it's going to be quite difficult. So what we do instead is we graph the negative of g of x and then add them. So really what we're doing is we're going f of x plus minus g of x. Now g of x is a parabola, x squared, it looks like that. Minus g of x is just the parabola flipped upside down. So we've got that, and that's minus g of x. Then we're going to graph f of x, which is x plus 1. That's 1, that's minus 1. And that looks like that. Now we can add them. We're just going to add this graph like we did in the adding functions part that we just learnt about. So we just need to add them. So for example, I always like to start on the y-axis. 0 plus 1 is 1. Again, we need to find where on the graph does it look like they're about the same. I'm feeling, oh, not quite there, maybe a bit further. Maybe here? It's probably going to be a bit further along. Let's extend my parabola. Maybe about here. Yeah, that looks pretty good. So what I've done is I've found the point, what we've been doing in the past. I've found the point on both of my graphs where the y value is kind of opposite each other, or they're equal in magnitude but opposite in sign. You might have heard that saying in physics when you talk about velocity. But we've found the point where my blue graph's y value equals the negative of my red graph's y value, and that means I'm going to have a y-intercept of about here. Again, it's going to have to go out like this and down because my parabola is decreasing so much faster than my linear graph is increasing. So when I add them together, it's going to have to be below the x-axis because, as I said again, if we look at, say, my parabola all the way down here, that y value is so much larger than this y value, so my graph is going to have to be down here. probably even going to be more dramatic than I drew it. Yep, so we've got that. We agree that a parabola trumps a linear graph, so it kind of has to go in the negative direction. Same idea here, it's going to be even more drastic. Let's consider the point where they look about equal. I reckon that's, oh, that's not the pencil. I reckon that looks like the point where they're equal. Right about, oh, maybe not. It looks like it's about potentially here, that they look like they're pretty much equal. It's going to be around there. That's where they're equal, and that's where my intercept's going to be, around there. And then, well, this has to go down like this. Has to be like that. Because I've got two negative graphs. For example, over here I've got about -1, and down here I've got like -10. If you add them together, you get -11, and you're all the way down here. So when you've got two negative graphs, they go down even quicker. When we get to the product of functions, when we have two negative graphs, they actually become positive. So your graph would move down from the third quadrant up until the second quadrant, because two negatives multiplied together equal a positive. So that graph is going to look something like that. I just need to check that in GeoGebra, just because I'm anxious it's wrong, but I'm pretty sure it's right. Yep, that's right. Cool. Now, what you should do as well is your graph is not going to look as bumpy. Your final graph's not going to be that bumpy. It's just the reason it's bumpy is because we've just done rough sketches. So what you then need to do is then draw a nice, beautiful graph over here and go, oh, okay, kind of looks like a parabola. It's going to be about here and then over here, and it's going to look a bit, whoop, that's awful. It's going to look a bit like that. So that's the subtraction of graphs. The subtraction of graphs, very similar to the addition of graphs. Remember, I'm naming these. Very similar to the addition of graphs, but instead, we graph the negative and then add f of x plus minus g of x like we would normally add in graphs. Okay, hope that makes sense. For those of you who missed out on this lesson, I hope the video makes sense. Please email me if it doesn't, and then we can go over it on Monday before you product of fractions. Product of functions. Alright, see ya.